Okay, well, it is my very great pleasure to introduce Ioanna Psaradaki, whose name, I'm sorry, I'm not probably mangled somewhat, but she comes to us originally from the observatory in Crete, and then went to the University of Amsterdam, but also Schroen, working with Elisa Costantini, as you can see here, on what is the sleeper topic of the decade. She has gotten in early on what I think is going to be a huge new field with the launch of CRISM, the mineralogy of interstellar dust, looking at the dust absorption in X-rays. Obviously, interstellar dust is a topic of great interest to many people, but it's really been slow to grow in the X-rays, despite the fact that there's a huge amount of interesting stuff you can learn, because the X-rays actually penetrate the dust, unlike the UV or infrared that just is coming from the surface of the dust. So there's a lot we can learn from this, and I think we're just on the verge of some major breakthroughs. She's got some of the most interesting results I think I've seen in this field in the last couple of years at the very least. So with that introduction, she's now at the University of Michigan working with Leah Corrales. I encourage you to lend your ears to what Ioanna has to say. Thanks very much.
Thanks for the introduction, Randall, and thank you very much for inviting me to give this talk. It's a great pleasure. So I will speak about interstellar dust mineralogy and focus on how we study through the X-ray band. But first of all, I want to motivate the subject and set the stage. So this is our galaxy seen through Gaia satellite. And as you can see, most of the gas and dust is distributed along the galactic plane. And darker regions across the galactic plane correspond to foreground clouds of interstellar gas and dust, which absorb the light of the stars that are located further away behind the clouds. And this, we know that basically most of the gas and dust we can find is near the galactic plane. Now, interstellar dust is obviously the protagonist of this talk and is characterized mainly by three things that we study nowadays, especially with the X-rays. One is the chemical composition, what's the chemistry of interstellar dust. The other is the size distribution of dust grains. And the last is the lattice structure. And by lattice structure, I mean how the atoms in the grain are organized. So briefly, we can divide into two categories. One is the crystalline dust, where the atoms are organized nicely. And the other is the amorphous, where we have a disordered network of atoms. And usually the typical dust sizes that we see are about 1 nanometer to 0.5 microns. And also I want to point out here that dust occupies about 1 to 2% of the total mass of our galaxy, but it's really, really important because of a few reasons. So why this is important to study? First of all, it's important for star formation. Dust grains keep interstellar gas clouds cool by absorbing the energy from both gas grain collisions and UV radiation, and these heated grains later emit the energy in the infrared. Second, dust plays a very important role for molecule formation. The surface of dust grains act as little factories that they bring atoms together that otherwise maybe not rarely meet, and they catalyze their reactions. Another magical thing about dust grains is that if we assume that their shape is elongated, what we know today is that they align their short axis with a galactic magnetic field. And this has enabled the studies of the direction of the plane of the sky magnetic field and its strength. So we can, for example, test different star formation theories. Well, sometimes dust is a bit annoying to astronomers, because when you want to study, for example, the cosmic microwave background, maybe you want to get rid of dust. And also dust is really important, a very important ingredient for planet formation, because we see some of the elements that compose the diffuse interstellar dust also in, for example, protoplanetary disks. Now, one of the clues that we have of what type of dust we expect to see in the ISM comes when we study the elemental depletions. And by that, I mean how much of its element is not found anymore in the gas phase. So it should be in another form, probably dust. And this is what we see in this plot here. So it shows for a few elements, basically the observed depletion of these elements, and as a factor of how the total depletion for all the elements is progressed collectively. So we can see, for example, that for carbon and oxygen, we have mild depletion, and magnesium, silicon, and iron are highly depleted. So we expect to have these elements in another form, possibly dust. Please note that despite that oxygen is only mildly depleted, this doesn't mean that we don't have a lot of it in dust. Oxygen is really abundant element in the galaxy. So even if a small amount of it is missing from the gas phase, it's still a lot to be included into dust. So today we know also from both X-ray and also infrared observations what dust is made of roughly. So we know that it's composed by carbonaceous material and silicates. So silicates is an interesting group of minerals that is mainly, we can mainly find there magnesium, silicon, oxygen, and iron. And we can roughly divide into two main groups, the olivines and pyroxenes. Please note that for olivine, we have 4 atoms of oxygen, while for pyroxenes, we have 3 atoms of oxygen, which is now an ongoing area of study to understand which of these 2 types of silicates is the dominant one in the ISM. Also, we can have oxides of silicon, magnesium, and iron. For example, magnetite is one of them. Sulfates, some sulfur bound with iron, and also metallic iron. And these elements that are found in interstellar dust are also basically elements that we find in the crust of our planet, the Earth. So now, I'm going to talk about a couple of open problems that there are today in interstellar dust mineralogy, and I will start about the oxygen, the element of oxygen. So oxygen is one of the most abundant elements, as I said before, in the galaxy, really important for life here on Earth. And we know today that it comes in many different forms, neutral, can be molecular, ionized oxygen, and also it can be in dust. So what is the problem? There is a problem that is called the oxygen budget problem in the ISM. Basically, this is illustrated in this plot, where in denser environments of the ISM, the combined contributions of CO gases, ices, and dust, silicates, and oxides, basically, cannot account for all the oxygen that we expect to see according to some standard values. So where is it, in which form? And this is mainly in the denser environments of the ISM. Now, let's move to iron. It's still unclear today what form iron takes. We know that a large fraction of it is locked in dust grains, 90% or even more. However, most of the iron that we know that is formed in supernova type 1a, as illustrated in this plot here from the literature. So basically, if we focus on the iron part, it shows that most of the interstellar iron comes from supernova type 1a, and much less of it comes from other sources that give dust in the ISM, core collapse supernova or AGB stars. And it has been hypothesized that most of it is ejected in the ISM in gaseous form, so the depletion should take place in the ISM. And the question is how it gets condensed into solids and which form it takes. What are basically the chemical formulas that include iron. So we know that iron can be found in silicates in the forms of olivines or pyroxenes. It can be also in metallic iron, either in free metallic iron particles or inclusions in silicates. We can have iron in oxides such as magnetite, which has ferromagnetic properties. And in the literature, there are some alternative iron carriers, such as hydrogenated iron nanoparticles. So the question is, are interstellar silicates iron-rich or iron-poor? And what is the magnesium to iron ratio, basically, in silicates? Now, can we get some answers to these questions from the X-ray bands? Well, yes. The idea on how to study the interstellar medium and interstellar dust is known for many years now. There is a number of studies. In our galaxy, we have a lot of bright background X-ray sources. We usually choose low-mass X-ray binaries. The light are way into the interstellar medium that has both gas and dust. And what we observe with the X-ray satellites is an absorption spectrum that has both the information of gas and dust in the line of sight. Now, a little bit about the physical process behind it. We know that below 10 keV, the main interaction of X-rays with matter is the photoelectric effect. Let's take this first case here, where we have an atom, gas basically. An incoming X-ray photon will remove one of the inner orbit electrons. The resulting cross-section, basically the absorption probability, has a sharp shape at the binding energy of that removed electron. Now, let's go to the case that we have dust, solids. The situation is a little bit different because the outgoing photoelectron will interact with the neighboring atoms. So it will modify the wave function and will create, because it will be constructive and destructive interferences, basically, and we will get around the photoabsorption edge a pattern, which is basically the fingerprint of interstellar dust. It shows what are the dust properties, the structural dust properties, and these are called X-ray absorption fine structures, and that's what we want to study. So X-ray absorption fine structures give us information about the chemistry of interstellar dust and the crystallinity, and also the size. This is an example here that illustrates what I just said. So let's go on the right plot. Let's start from here. So these are models of XAFs in the silicon K-edge. So we have two different types of silicates here, and as you can see, the XAFs pattern is different. And if you go in the middle panel of this plot, there is a crystalline versus amorphous model, and as we can see, when the crystallinity is distorted, then we lose this this very fine structure of the XAFs. And in the first plot, we see here two models, cross-sections, dust cross-section, the silicon K-edge, produced with different dust size distributions. And that's a proof on how we study also the dust sizes. Here we see some large grain population in blue compared to some smaller grain population in red. And this peak here is called the scattering peak, basically, and this is the indication of our size distribution. So let's see an example on real data on this. This is a Hg spectrum around the silicon K-edge, and you can see atop a gas model. And these wiggles around are basically X-ray absorption fine structures, and this indicator will be for our dust size distribution. So now, one of the power of the X-ray band in the study of interstellar dust mineralogy is that we can probe many different astrophysical elements. Basically, we can directly probe the photoabsorption edge of the elements that are expected to be in interstellar dust, and because of the transmission of X-rays is dependent on the column density of the ISM in the line of sight, we can also study different ISM regions. So for example, if we want to study more diffuse regions in the ISM, or if we want to study the carbon and oxygen K edges, we need low column densities of the ISM. And for example, for silicon and magnesium, we need some higher column densities, about 10 to the 21. And if we really want to probe dense ISM, we need to study the iron K edge, which is what Athena will be great about. I'm going to talk about at the end. So, so far, we have two great instruments that provide us with wonderful spectra to study also the interstellar medium. And we need actually to use the high resolution X-ray spectrometers on board XMM-Newton and Chandra satellites to study these weak absorption dust features. So in the literature, there are many studies so far. I'm going to review a few of them, and then I will give a few recent results that we have obtained. Basically, the oxygen K edge has been studied by both Chandra and XMM-Newton. And here you can see some studies where only the gas phase oxygen has been assumed, while here you see a study where also dust absorption has been, with XMM-Newton data has been used. Iron L edges have been also studied extensively. Again, here this is an XMM-Newton spectrum, and there is the dust absorption model, and also later on using Chandra HDG spectra and including the scattering component of extinction, there were further studies about that. And of course, there are some older studies that basically have identified XAFs in the silicon K edge and also other elements such as magnesium that I suggest you to check. Now, in order to properly study the X-ray absorption phase structures, we need dust models. And to do that, we basically need to go to the laboratory to obtain X-ray spectra of dust and then produce our models. I'm going to skip this. So in the literature, there are already some models, such as those of Li et al. But what we needed was a more self-consistent dust extinction model that accounts for all the photoabsorption edges. So for this reason, we went to the laboratory. This was a group effort at Electron, and we basically measure all these elements: silicon, iron, magnesium, and oxygen. And this was used to build a unified dust extinction model that, as you see here, this is not a realistic example. This is just for illustration purposes to show that basically what we have here is we can have a model that accounts for all the different photoabsorption edges. Some of these, for example, silicon magnesium are already, some of these models in the specs X-ray fitting package. But stay tuned, before the launch of CRISP, we hope to have also oxygen and iron L. So I want to show you a few examples of these measurements, first in the silicon K edge. As you can see here, these are a few of silicates that were measured using synchrotron facilities. And basically, you can see that the different silicates produce a different XAFs pattern, and this is what will give us the answer from when studying the X-ray spectra. This is a Chandra HDG spectrum, and we see that basically the total model is the total best fit model is a representation of some silicate, olivine gas, and also some quartz, which is a silicon oxide. So from this study in silicon and magnesium edges, there were some results so far. So amorphous olivine that has this chemical formula with 4 atoms of oxygen basically represent most of the dust mass in the denser environments of the ISM that we probe with the silicon and magnesium edges. And also, next I will move to talk more about oxygen and iron, basically, that I present the problems that we have in the beginning with that. So I want to talk a little bit more in detail about the experiment there that I was involved into. So we visited an electron energy loss spectrometer, some facilities that are located in South Spain at the University of Cadiz. We had about 20 test samples that you can see here, these small flasks with the little powder, the interstellar dust, that are silicates with different magnesium to iron ratio, oxides, and as well iron sulfates. Some of them are natural from meteorites or were also synthesized in a laboratory in Vienna. And most of them come in both crystalline and amorphous form, so we can study the crystalline to dust grains as well. So the first part of this work to go from 0 models to fit your X-ray spectrum is, of course, to take the spectrum in the laboratory. So here you see how the dust grain will locate we try to locate the dust grains in a small carbon grid so that we place it inside the microscope. There is an electron beam that interacts with the dust samples, and what we measure is the change of the kinetic energy of the electrons because of the interaction with that dust sample. And we get what we call the electron energy loss spectrum, that you see a raw spectrum from the laboratory here. And basically we get the fingerprints of dust in the oxygen K and iron L edges. This experiment we did for all the different dust samples. And here you see an image of the dust grain, or the region of interest on the dust grain, how it looks with the microscope. And the color code basically is the thickness of the grain. So great, once we have our laboratory measurements for all these 20 dust samples of different chemical composition, what we need to do is to translate them to a quantity that we understand as X-ray astronomers, and this is the dust extinction cross-section. So from the laboratory, we do a computational part. I won't talk about in detail about it now, but briefly, what we need to do is to calculate the complex refractive index, the optical constants, and then we calculate the scattering, extinction, and absorption efficiency. And later on, we also assume a preferred dust size distribution to calculate the total extinction, dust extinction. So once we have the, you can see an example here, assuming an MRN dust size distribution on the left in the oxygen K edge. And also there are some preliminary results on how the profile of the extinction curve changes when we assume larger grains than the typical MRN dust size distribution that we assume. So basically, MRN is a size distribution of a very typical dust size distribution where we use nowadays with this size. And what we notice is that basically the scattering component of extinction, as you can see here, becomes larger as the grains become larger. So that's a clear indication again that we can start probe the size of the dust grains. So once we have all these cross sections, we need to feed them to a favorite X-ray fitting package. In our case, we used Specs that is designed in the Netherlands. But these models eventually will be public to be used also in any other X-ray fitting package that we use nowadays. And the last step is, of course, to having those models into the X-ray packages to fit our spectra. So we need to choose the X-ray sources. We need to choose bright sources along the galactic plane to have basically a lot of dust. And one of the criteria, of course, is the availability of data in the Chandra and XMM archives, and also what is the column density, because depending on the edge that we want to study, we need to pick column density. So we chose a number of sources along the galactic plane, and we came with some results about the dust mineralogy by studying both the oxygen K and iron L edges together. So in these diffuse ISM regions that we probed, we found that the magnesium-rich amorphous pyroxene with this chemical formula is a dominant compound, dust compound, but also we found metallic iron as well. And we found an upper limit of 15% of crystalline dust. A lower upper limit has been found from the infrared. Strictly speaking, because we find upper limits, we are consistent. But if we want to basically explain why we have this, we're not consistent with what we find with the infrared, but we find a higher amount of crystallinity. This is probably because X-rays penetrate the grain, and we maybe can see crystallinity in some partially glassy materials. So that might be also one of the power of the X-ray band by studying interstellar dust mineralogy. And what about the oxygen and iron abundance and depletions? We found that about 10 to 20% of oxygen is in dust. We expect that oxygen is mildly depleted, but still it's a considerable amount. And we found more than 90% of iron in dust. Basically, iron, as we expect, is very highly depleted. So now, in the last minutes, I want to talk a little bit about the X-ray future missions that we all look forward to. I will speak about 2-3 missions also include, and I will finish with how Athena will complete this picture that we have of interstellar dust and how important it will be for some particular problems. So first, this is a plot that shows what is the line detection capability of current and future instruments. So this is basically the square root of the effective area times the spectral resolution. So we can see basically where is here the XMM-Newton RJ. So it's better to study oxygen, that is about here. We also see here Chandra. And we see that basically CRISM will advance our knowledge and we'll have much better sensitivity, especially around the silicon key edge. There is the concept mission of Arcus that basically will be great in the oxygen key edge. I'm going to show an example in a while, but Athena will advance our knowledge even further. It will be a super instrument, and you can see here how much higher line detection capability we are going to have. I want to briefly mention about Arcus. So basically, this is a simulation with the Arcus response matrix at the oxygen key edge. And basically, we can see here that we can see a forest of lines, basically, of different ionization temperatures at the ionization species of oxygen. So we can study not only the gas and dust separation, but also we can see the different phases of the ISM from just the spectrum in the oxygen key edge. And also possibly, and hopefully with such an instrument, we can also study kinematics of different gas components. Now, soon next year, there will be CRISP, will be launched spring next year, hopefully. And with CRISP, we will have a great sensitivity in the silicon key edge, and we will be able to study silicates in very, very great accuracy. Here you can see an example, a simulation in the silicon key edge. And this is the data represent basically gas, and on top you can see different dust models, and you can see how you can separate, but also you can separate the different dust size distributions. And here on the right, you can see an example, a simulation of the sort XRT+1 that is also a CRISP PV target. And you can see here that basically this source is known also for a highly ionized absorption. So with CRISP, we will be able to not only study the different dust minerals, but also the different phases of the ISM, the different ionization phases around the silicon key edge. You can see here the transmission of different models that are fitted to the simulated data. And of course, Athena, that will basically, so Athena will be great for studying all the interstellar elements that I talked about before, but I want to focus on one particular reason why we really look forward for Athena, because we will be able to probe with great accuracy the iron key edge. So far, we can study diffuse and maybe mildly dense ISM, but with Athena, we'll be able to probe the iron key edge. And this is great because we can study dense environments of the ISM. Well, basically, if we're lucky enough to find the great sources, we can probe maybe a source behind the molecular cloud. That's what I really hope for. And we can study what is the dust grain chemistry over there. And this is a simulation in the iron key edge with Athena. You can see here the gas, basically the simulated are assuming only gas. And on top, you can see the different dust model that will be able to separate. But also through the iron key edge, we can also, and Athena, we can also study the different size distributions of dust grains. So we really, really look forward, especially young researchers, I see, for all these great missions and also for Athena. So, and with that, I'd like, last thing before I finish. So it's not only going to be great for the iron problem of the ISM, but also for the oxygen problem, because by probing dense environments of the ISM and by understanding what silicates fit better in the iron key edge, we can guess how many atoms of oxygen are in the silicates, and basically we can understand how many of those are in dust and maybe provide some answers to the oxygen budget problem. And with that, I'd like to finish and leave you with my conclusions. Thank you.
Thank you. Wonderful tour of the field. Okay, we will take questions via the chat or Q&A feature, if you'd like to. I will start off with, you showed the lab measurements and a lot of variation with the different solid state structures of the silicates and amorphous versus crystalline and so on. Did you ever experiment with basically taking two of the same samples or multiple cases of the same samples? Is there variation even amongst what you think is the same sample, or is it really quite constant for the same type of dust? But what I'm wondering about here is that do minor variations in the samples lead to big changes, or is it really it's got to be a completely different structure in order to change the X-ray response?
Yeah, so we do take a few, basically 5 to 10 measurements for each dust sample. And then we basically, for the final cross-section, we calculate the average basically. But of course, we check for variations between those. And of course, to sum them up. And basically, the variations are due to the different chemical formula, due to the XAFs.
Okay. So we may get to the point of having to think about what forces in the universe are forming the dust, and therefore what kind of structures we'd expect to see and what ratios. I mean, it seems like, you know, there's obviously a lot of different ways to put silicon together. So, and we can't expect that there's just going to be one particular molecule that we see. So like the analysis sounds like it's going to get complicated.
Yeah.
Oh, and I really like that Arcus mission you showed. That looks really interesting.
Yeah, actually.
It's a great simulation.
I really love it. Yeah, because we can see, because this is, I didn't show that before. This is RGS spectrum in the oxygen key edge, which is really great. We can even now probe with RGS the multi-phase ISM, but yeah, with Arcus, the development will be enormous.
Yeah. Okay. Any other questions? We've got a few minutes left. Don't be shy. Matteo, or Matteo followed by Didier.
Yeah, thank you. Very interesting and really indeed a splendid simulation. So also the Arcus one. My question is, you mentioned at the end for Athena both oxygen and iron. So if somebody would ask you, you know, I can give you breakthrough performance only in the soft, either in the soft or in the hard X-ray band, for which element would you say that Athena is likely to give the most important breakthroughs, the one that are likely to be unsurpassed to come for decades?
Thanks for the question, Matteo. That's a really nice question. Looking at this, and also having in mind that the iron key edge, we actually need to study the iron key edge, and we will be able to study with CRISM, but with Athena will be even better the sensitivity. So having this in mind, I would say I would focus in the iron K personally. So yeah, basically this study here, because also the iron problem in the ISM, it's huge. Now we are studying the iron L edges in the soft band below 1 keV. But it would be really, really great if we are able to study the iron with Athena, iron K edge, and compare these results, because with the iron L edges, we can understand the iron inclusion in dust in the diffuse ISM, and then with the iron K in the dense ISM, and then we'll have a much better probe of what's happening with iron.
Excellent.
I hope I replied to your question. Yeah.
Yes, perfectly. Thanks a lot.
Didier? You're still muted.
Yes. Thanks for the talk. Very nice. I really enjoyed it. I have just a couple of questions. One is what you to do that with CRISM. I think CRISM must be able to observe very bright sources. Will there be a limit beyond which you won't be able to go with CRISM, and this may hamper some of your observation? That's the first question. The second question is, if I take your previous answer, among all the parameters that we have to preserve in the reformulation of Athena, for you, the high energy response is the most important parameter we have to protect, together with the spectral resolution and the capability to observe very bright sources, because the GX3+1, for instance, are very, very bright sources. So putting a calorimeter in front of these sources is, it implies the capability, for instance, to decode, to defocus the optics, for instance.
Thank you. So I had at some point an interruption to the connection, so I hope I understood the questions clearly. So the first was if with CRISMs we need bright sources, and if this is a limitation to study the silicates or the iron. So CRISM, so let me go back here. Already in the PV targets of CRISM, there are we need bright sources by default to study the X-ray absorption of high structures, and basically with CRISM we will have this possibility, and there are already in the PV phase 2 sources where we can study silicates, and one is this one. Basically, the best is, yes, to have bright sources to study the XAFs. And the second question was, could you please repeat?
Yeah, no, I mean, your second question for you, the most important parameter is indeed the high energy response, the 7 keV response, together with the spectral resolution and the capability to observe very bright sources with X-ray view. So it means that to do this type of science, we must keep, for instance, the defocusing capability of the optics. And we must boost the high energy response, possibly with multi-layer coatings of the optics.
Yeah, so let me think. So for sure we need line detection capability, because X-ray absorption of fine structures are weak features compared to, for example, some very highly ionized absorption lines. And we need to be able to distinguish between dust models. So this is really important. Of course, we need good signal to noise as well. So I would say a good combination of both. That's why I like to plot in this way the figure of merit, because it shows, yeah, basically for me, both of these things are important up to a degree.
Thank you very much.
Thank you. Excellent question. Okay, are there any other questions up? We have one other one from Nanda.
Hello, thank you very much for the extremely nice talk. I have a more general question about the oxygen problem that you spoke about, which is indeed something which is important over several field research and several bands actually. So my question is how, maybe I think you said it, but I didn't get it exactly. So how X-ray spectroscopy is actually unique in this? So what can you do about this problem with X-ray spectroscopy that you wouldn't be able to do in the millimeter or in the infrared in other bands?
So basically, I'm going to go probably here or maybe here. So first of all, we have the photoabsorption edge of oxygen in the X-ray band that we can study with nowadays with RGS, and because oxygen is mildly depleted in dust, it's important to have also to study together the gas phase, ISM together with the dust, and fit those components together with physical models that luckily we have nowadays. So we can do this with the oxygen K edge. This is one advantage. Another thing is that because, for example, we know that most of dust is in silicate composition today, and the best thing is to study not one element alone, but also elements together. For example, in our study, we studied oxygen and iron together, we fit those edges simultaneously despite being with different instruments. So with X-rays, we can do that. We can basically fit different continuum and same ISM model and understand from two edges, not only one alone, two elements together, what's the composition of silicates. There are a couple of sources that luckily we got some data this year that we can study more photoabsorption edges together, silicon and magnesium as well together. So this breaks a lot of degeneracies, and this is really a power of the X-ray band. For example, I think iron we can only study directly from the X-ray band. So this is really nice because we can study the mildly depleted oxygen together with an element such as iron that is highly depleted. And another thing, as I said, that will be, I hope possible with Athena, and this is something I'm really curious to see, is by studying the dense environments basically, and the iron key edge, guessing how many, because when you fit a silicate model, this silicate model has also some atoms of oxygen, and depending which one fits better, you can see how many oxygen atoms. And this is really great because we can see in the really dense ISM what's basically is expected, how many atoms of oxygen in silicates. Yeah.
Okay, thank you very much. Thanks.
Okay, any final questions? Good discussion, excellent presentation. Many thanks to Ioanna.
Thank you.
With that, I will close our final webinar for the year.